Hi, everybody. Sorry about the delay. Show business, no business like it. My name is Anjana Vakil. Hello. I'm really excited to be back at JSHeroes the second time, 2 years in a row. You can find me on Twitter at my name, because I'm not creative with internet handles. And if you look at my latest tweet, you can see the slides that I'm actually going to go through. Well, not the slides, but the material, and then some. So this is going to be a experimental live exploration of the Lambda calculus, which we're going to talk more about what that is in a second, but I'm hoping that you all can do this with me as we, right now here, live on stage, dig into what I think is one of the most beautiful and elegant and interesting abstractions in the history of computer science. So before we jump into all that, just really quickly, some organizations and communities that I am so lucky and so proud to be a part of. So I work at Mapbox in San Francisco. Any Mapbox users in the house? A few hands? Cool. We make a location data platform for developers to build beautiful maps and navigation experiences and all kinds of location-powered apps. Check it out. I'm also a member of the Mozilla Tech Speakers. Mozilla Tech Speakers in the house? Woo! Yeah. We love to wander the world talking about open web technologies. Check it out. All of these things are linked in my Twitter bio, by the way, so you can find links there. I am also an alumna of the Recurse Center. Recurse Center is a programming retreat in New York City. It's free, it's self-directed, it's a wonderful place to go and learn more about programming, get better at coding, whatever that means to you. Check it out. And finally, I'm an alumna of Outreachy. Any Outreachy alums in the house? Woo! Yes! All right, so Outreachy is an amazing initiative to get more women involved in open source by offering paid remote internships at organizations and projects like Mozilla. So if you know somebody looking for a paid remote internship who is a woman and wants to get into open source, check out Outreachy. All right, whew. So I said I'm here to talk about the Lambda calculus. The what a calculus? The Lambda calculus. So this is too big. The Lambda calculus is lambda, like the Greek letter lambda, this triangle-y looking thing with a little sprout on the top. Yeah, that. You might recognize that symbol from the logo of every functional programming language ever, like Haskell and Clojure. And that's because the Lambda calculus is kind of the abstractions and the formalisms of the Lambda calculus are really foundational to all of the practice of functional programming that we know and love today. But it goes way back beyond that. So this was a mathematical and logical formalism created by this dude, Alonzo Church, one of my heroes, back in the 30s, beginning in the 30s, and he was trying to investigate the nature of logic and mathematics and giant philosophical concepts like that. Love it. And he created this system, the Lambda calculus, and basically fell down this huge wormhole with all of this stuff, like the nature of logic and computation. And we collectively, as a discipline in computer science, and particularly the functional traditions in computer science, have been collectively falling down that really interesting rabbit hole for the last, going on 100 years now. So this is a really cool, interesting way of representing computation. And what's so cool about it, I think, is that the Lambda calculus is founded on just one tiny little abstraction, one tiny construct, and from that we can model anything computable. Anything a Turing machine can do, this thing can do, this one little thing. And in our case, we're going to do it in JavaScript using an arrow function, so one arrow can recreate all of computation. So no big deal, you know. In any case, what we're going to do today, we're going to play a little game. If we treat a JavaScript arrow function like a Lambda calculus Lambda function, what can we do? What can we make with it? I've already given away the answer, everything, literally everything in computation. But just because we can do computation this way does not mean that we should do computation this way. So this is not going to be a practical programming talk. In fact, this is going to be the most useless talk you see at this entire conference. Do not go back to your boss on Monday and try to suggest that you all write code in Lambda calculus. No. This is not about practical programming. This is about expanding our idea of how computation can work. So what we're going to do here is going to be pretty silly, it's going to be pretty experimental, but hopefully it's going to help us all think about computation in a new and interesting way and expand our brains a little bit. So that's the idea. If you'd rather be learning practical programming stuff, I won't be offended if you step outside or put in those earbuds and start Googling all the cool frameworks and libraries you've been hearing about today and yesterday. So no worries there, but what we're going to do here is going to get a little silly. All right, so I said let's use an arrow function like a lambda function. What does that even mean? What is a lambda function in the lambda calculus sense, not the AWS sense? Nothing to do with that. So basically, in the lambda calculus, we have a way of making functions that syntactically looks a little different from what we're used to. So can y'all see my pointer here? So in the lambda calculus, we use the lambda symbol, and then some variable, in this case like x, would represent like an input to this function. Then we have a dot, and then anything to the right of the dot is basically the body of the function. So right here, we're making a function that is essentially the identity function. So it takes in some input x, and it returns x. And that's how we would represent it in lambda calculus syntax. How we would represent it in JavaScript arrow function syntax probably looks a bit more familiar. We have the input to the left of this equal sign greater than this arrow, and then whatever we want to return directly following that. Now, we could have parentheses around that input x, but if we only have one thing, we don't need them, so for cleanliness' sake, we're just going to leave them out. And this is so that what we've done here in the lambda calculus, this is sort of like declaring a function, but in lambda calculus, that's called function abstraction, because everything in functional programming has to have a fancy technical term. So if you hear function abstraction, that's what that's about. And here's the thing about the lambda calculus. Unlike JavaScript arrow functions, which allow us to have however many input arguments we want, if we use parentheses and commas, in the lambda calculus, we only get one input to each function, one argument. So if we want to do something that like conceptually requires multiple pieces of information, like let's say adding together two numbers, we have to kind of layer these lambda functions or chain them together. So what we do is we create a function that takes in one of those numbers, the first one, x, and that returns, so everything to the right here, that returns another function which takes in the second number, and that returns then the addition of the two. Cool? So if we want to take in multiple inputs, we need to chain these functions together this way, and we can do that in arrow syntax as well by having an arrow function that takes in x and returns an arrow function that takes in y and returns x plus y. Everybody on board? Okay, so we're going to restrict ourselves to this. This is like the game that we're going to play. And then we also, it's not enough to just like create functions all over the place. We want to use them eventually. In lambda calculus speak, that's called function application, basically calling our function. In the lambda calculus syntax, what we would do is we would have the function and then a space and then the values that we want to apply the function to, or the values that we want to call the function with in regular programmer speak. And in JavaScript, that's going to look pretty much the same, except instead of having spaces to indicate the values that we're passing in, we're going to use parentheses to say, okay, I'm calling this function here on 5, and then that's going to return another function, right, because we're taking in this y now, and then we're calling that on 1. So this is just syntactically, it looks a little weird because we're used to passing in arguments with like commas, right? But this is just we're gonna play this syntax game. We're gonna do it this way. On board? Cool. All right. Awesome. So now we know the rules of the game. What can we do? How about we make some numbers? Because programmers like numbers, right? Numbers? Like them? Yeah. Woo, numbers. How about counting with whole numbers? Counting is fun. We can count things. That's cool. All right. Counting is useful. What can we count in a world where all we have is the concept of a function? We don't have any other data types. We're starting from scratch here. All we've got is this idea of functions with single inputs and single outputs. I'm going to let you think about that. What can we count? We can count functions, but we want to be able to like do things with this, right? So when we're talking about like running our programs, what we can actually do is not count the number of functions that we've created, but actually take a single function and apply it a certain number of times, or call it a certain number of times, and we could treat each call to that function as like counting one more. So I call the function once, I count 1. Call it again, I count 2. Call it again, I count 3. So we're going to count function applications, or calls to the function. Okay, so that means numbers are going to be things that apply functions a certain number of times to inputs. This is going to get weird, so buckle up. All right, so if I want to make a numbery type thing, it's going to be a function, because everything is a function, and it's going to be a function that takes in some other function, f. And then that's going to return a function, because everything is functions, which is going to take in some arbitrary input x, and then do something with it. I don't know. What we can do, so all numbers are going to kind of have this structure, this shape of taking in a function, and then that's going to return a function that takes in some input and applies the function a certain number of times. So like if I wanted to count 1, what I would do is apply f once, so call it once on whatever that input is, x, okay? And if I wanted to count 2, I would apply f twice, call it twice on that function. Any guesses what 3 is going to look like? Help me out. F of x, 3 f's, cool. And 0? So if I want to apply f 0 times, then I can just return x. Boom. Okay. Whoops. So now, these personally, I don't think look that much like numbers. Do you think they look like numbers? Yeah, I did not when I first saw this. So I had to convince myself, and I'm going to try to convince you too. So how do we know these are numbers? Well, let's cheat a little bit. Let's make a function that converts these lambda numbers into JavaScript numbers by creating a function called toNumber that takes in some number n and then applies n to a function f, which here is just going to take in some whole number and add 1 to it. And that's going to give us a function that then we can apply to some input, and if we apply it to 0, then if we take this function f here and apply it once, we're going to add 1 to 0 and get 1. And if we apply it twice, we get 2. If we apply it 0 times, we're just left with 0. Everybody on board? Okay, so if this is our little cheat, it's cheating because we shouldn't have access to these actual JavaScript numbers, but it's just cheating for sanity. Okay, so I should be able to run this on one of my numbers, like 2, let's say, and get 2. And what if I try it on 3? Oops, well, what happens if I spell it right? I get 3. And if I try it on 0, I get 0. Oh my God, y'all, we just made numbers. Cool. Okay. So we have some numbers, and actually there's a fancy Googleable term for these called church numerals. Remember my bro Alonzo? Yeah, so these are named after him, representing numbers this way. Church numerals. Have fun Googling it. It will lead you down a very deep rabbit hole. It'll be awesome. Okay, so now that we've got some numbers, what else can we do? How about some arithmetic? Yes, we're entering kindergarten. Awesome. Okay, how can we add two numbers n and m when each of those numbers represents calling a function a certain number of times? So let's say n is 2 and m is 3. N represents calling f twice, and m represents calling f 3 times. How can I add those two together? Think on it. I couldn't hear that, but that's cool. We're gonna go through it together. So what we're gonna do, if n is 2 and m is 3, and I want to get to 5, I'm gonna call f n times 1, 2, and then I'm gonna call it m more times 1, 2, 3, together should give me 5. So let's make an add function. Okay, what is this function going to take in? Well, it needs two numbers to operate on, but we only have a single input at a time. So we're going to take in a number n. We're going to return a function that takes in a number m and returns what kind of thing? What kind of thing do I want this add function to return? Well, yes, a function, but okay, what kind of function? Like, if we add two numbers together, we expect to get out another number. Okay, and what do number functions look like? They take in a function, and they take in some kind of input, and that's the shape of number functions, right? So what we're doing here is returning a number-y function thing. Okay, cool. So now we said first we need to call the function f n times. We do that by applying n to f, right? And applying that to our input x. So this calls f n times, yes? We're on board? Okay. Now I need to call f again m more times. So what if I treat this whole thing as like that x input, and I call that function f m more times? Huh? I know you're all like, yeah, that's exactly what addition looks like in my head. Yeah, me too. Okay, now, I should now, if this works, which it's live coding, I don't know, we'll see. If this works, I should be able to create a number like 4 by applying add to 1 and 3, right? Oops. And I should be able to then convert 4 to a number and get out 4. Oh my God, it worked. Alonzo, everybody, amazing. All right, now I could have rigged that. You don't know what's happening here inside of my computer, right? So let's try something else. Let's try like adding 2 and 3. We get 5. Oh my God, what if I swap them? We did it! We added numbers together. Is that the most exciting thing ever, or what? Yeah. What about some more arithmetic? How about multiplication? So what if we want to multiply n and m? So if n is 2 and m is 3, I want to call f n times, so 1, 2. And that's kind of like one round of calling f n times. Then I want to call it again, right? 3, 4, that's like 2 rounds of calling n. Then I want to call it again, 5, 6. That's 3 rounds. So that's like 6 being the composition of n is 2 and m is 3. I'm calling the function n times m times over. All right, we're going to think about what this function should look like if I want to make a multiplication function. What is this going to look like? I'll let you think about it for a second. All right, so it's going to have a pretty similar shape to the previous, the add one, right? It's going to take in one number, and that's going to return a function that takes in another number, and that whole thing is going to return a number, so we're going to need some more of these. A little bit of boilerplate in the Lambda calculus. All right, now we said we want to call, first of all, we need to call f n times, which we do like this, right? Now, because everything is functions here, the application of n to f, that's just another function that calls f n times, right? So what if I treat that as my new f that I call m on? So now I'm taking this function that calls f n times, whoops, and calling it m times on my input. It makes total sense, right? Okay, all right, let's see what happens. I don't know, it might be wrong, let's find out. So if I did this right, I should be able to multiply two numbers, like 4 and 3, together, and get, oh my God, okay, wait, does it work in the other direction? I don't know, let's find out. Cool, okay, and like, am I rigging this? No, it even worked with different things that I typed in right in front of you. Oh my God, y'all, we just added and multiplied numbers that we created from scratch. This is like the pie that we just baked. It's amazing. Now, we're not going to subtract or divide because those are like way harder. But they are doable. But even so, we should be proud of ourselves because even with these two little kindergarten functions of adding and, well, multiplying might have been first grade. Anyway, even with those, we can do some pretty cool computation. Like, we can think some real deep thoughts here, like, what's the answer to life, the universe, and everything? Well, if I add 4 to 1 and then multiply that by 2 and then multiply that by 4 and then add 2 to that, then I should get Woohoo! Yeah! Okay, cool. So now we've basically done all of computation. No, not quite, but suffice it to say that we can do like all of the arithmetic that we want here and even solve some real deep problems. All right, so simple math is cool, but I said that we can do all of computation with this thing. What else do we need to write programs? Like, we're programmers. What else do we need? Numbers and math is not going to cut it. We also need hooks. Yeah, eventually we could get to hooks, but not in the next 10 minutes. So what else do you need to write like a basic program? Ifs? Exactly. It's almost like I planted them in the audience. We need conditionals, right? We need control flow. And in order for conditionals to work, we need some kind of Boolean values. We need truth values, right? And these all kind of go hand in hand, Booleans and this control flow of ifs, right? So like thinking about ternary like if syntax that we're used to, we have some Boolean, and we evaluate it, and if it's true, then we want to do some kind of then clause that we're going to look into, whatever. And if it's not true, then we're going to skip right to some kind of else clause, yeah? So what we're going to do is we're going to define both the syntax of if statements and Boolean values all together in a way that this whole thing works out and is possible. Okay, so, I want to have an if-then-else statement, or like syntax, but everything is functions, so it's going to be a function. It's going to take in three things, right? We basically have three components here. We're going to have some kind of conditional, some kind of Boolean, and we're going to have some kind of then thing, and we're going to have some kind of else thing. But else is a protected word or a special word in JavaScript, so I'm just going to rename these to then and else. Okay, and then we're going to do something. I don't know what. All right, let's put a pin in that for a minute and think about these Booleans. Now, what do we want Booleans to do? Well, we want them to choose the right branch of our conditional here, right? So if I have a true in my Boolean spot here, I want to hit this then thing. And if I have a false in my Boolean spot, I want to hit, oh gosh, I want to hit, oh no. Okay, I want to hit the else thing if I have a false, right? So what if, and this is going to sound weird, but what if a Boolean were just something that takes a then and an else and picks one of them? So if it's true, I want it to pick the first one, the then, exactly. And if it's false, I want it to pick the else. So we're defining Booleans as like pickers. We give them two things, and they pick one of them. And which one depends on just we're defining truth values that way. So then, in my if, then, else, I've got a Boolean, I've got a then, and an else. What if I just apply the Boolean to the then and the else and let it choose which one it wants based on its truth value? Okay, let's see if this works. I'm pretty tired, so it might not. I don't know. All right, so we're gonna see if this could work. So as I said, I'm pretty tired. So if I had a value tired, I would set it to true right now. And the number of coffees that I'm going to consume today depends on my tiredness. Yes. So if I'm tired, then I'm going to have 3 coffees. I've already had 1. Got 2 more to go. If I somehow through this talk get so excited about the Lambda calculus that I'm no longer tired, then I'm just going to stick with my 1 coffee. Okay? So this is a little program I've written to tell me how many coffees I'm supposed to drink today. And it should tell me, oh my god, a number came out. So that number was 3, which is what I would expect if I am tired. Now, I am getting pretty jazzed about the Lambda calculus right now. So I'm feeling a little less tired. Let's see if this program still works. Y'all, we just got control flow from arrows. Just me that thinks that's cool? Wow, tough crowd. Tough crowd. Yay, okay. How about some logic? Now that we have Booleans, we can make operators that mess with them. So how about we just, to keep ourselves sane, we cheat a little bit again, and we just create another converting function to Boolean, which is going to take a Lambda-y Boolean and apply it to JavaScript's true and then JavaScript's false as the then and the else, and give us one of them so that we can just test, we can make sure that we're getting the right truth value we expect out. On board? Sound okay? All right, so I should be able to convert false to Boolean and get JavaScript false, and true should give me JavaScript true. Cool. Okay. Now, how about a logical operator? How about not? So, not is going to be an operator that operates on Booleans, right? So we want it to take in a Boolean. And then we want it to return a Boolean, so that's going to need to be something that looks like this, that takes a then and then an else. Yeah? And so, if I were just going to apply this Boolean to then and else, then I would get whatever the truth value of the original Boolean was. But I don't want that. I want the opposite of that. So let's get real tricksy and swap them. We are hackers, yeah. We're just gonna move these around, oops. And hopefully, I now have an operator that gives me the opposite of what I want, of what I originally had. So not true should give me false, and not false, true. We are so tricky. Oh my gosh. All right, I only have a couple more minutes. So what about some more logic? We're just gonna fly through these. So what about or? So or is gonna be an operator that operates on some Boolean A and some other Boolean B, right? Now, just for the sake of speed, I'm just gonna show you, okay, so let's see. So A is a Boolean, so that means we apply it to two things, a first thing and a second thing. Now, or is if I have A and I already know that A is true, I don't even need to look at B, right? Because I already know that A is true. So if A is true, it's going to pick the first thing, and we want the or operator to return true. So what if we just have the first thing be A? So that if A is true, it picks the first thing, and that's itself, and it's true because we just assumed that, so it returns true. And then if A is false, then this is going to pick the second thing here, and then the value of the whole or is going to depend on the value of B. So what if we just have it return whatever the truth value of B is? Because if B is false, then this is going to evaluate to false, and if it's true, then cool, we get true. All right, so if that worked, then I should be able to do an or on false and true and get true, okay. What if I do true and true? Okay. What if I do true and false? And the only time I should get false is, truth tables are hard. Yes! We did a truth table, y'all. It's pretty exciting. Now how about and? Any guesses? So, and is going to work in a similar way. So if these Booleans are things that choose things, all right, if A is false, let's say A is false. We already know, we don't even need to look at B. The whole thing is going to be false because A is false. So if A is false, it's going to pick the second thing. So what if we have it return a false value, and we have a good idea of what a false value might be because we just assumed that A was a false value? Okay, now if A is true, then cool, we can go on and look at B. And then the whole thing is going to evaluate to whatever the truth value of B is, right? So if A is true, it's going to pick whatever goes here. So let's have it return whatever the truth value of B is. Yeah? So now I should be able to do and on false and true and expect false. Cool. False and false, also false. True and false, also false. And I should only get true when I have true and true. We did more truth tables. Yes. Okay, so now we've got logical operators. Now we can do all kinds of stuff, right? Now, look at all of this stuff that we have been able to make with just arrows. We've got data, we've got numbers and Boolean values, we've got arithmetic, Okay, maybe not subtraction and division and the tough arithmetic like that, but I promise you can do it, just not in 37 seconds. Wow. We've got logic, we've got control flow, we've got like a lot of computers that we're able to mimic now. And so what we've done, representing data in this way, representing it in terms of how it behaves when you give it certain inputs, is called church encoding, so second Googleable term. You can Google church encoding to fall down an even crazier rabbit hole than the one that we've already been in so far. Okay, now, there's a lot more that we could do, but I'm like out of time, so we're not going to do it. We could subtract, we could divide. We could have successor functions that give us the next higher number, predecessor functions. We could do predicates like, is this thing 0? Is this thing even? We could do equality operators, inequalities. We could even, since we have numbers now, if we think about characters as really just being like the codes assigned to those characters, we could even represent strings as numbers. And we could have, we can actually create data structures, so we could create pairs of things, turn those into lists by nesting them, and then we can even make list manipulations like map, reduce, and filter, and then we're full-blown functional programming, yo. And from there, we can get all of computation out of this single arrow. That's so cool, I think. And even more mind-blowing, you know what else we can do with an arrow? We can do object-oriented programming. What? No, seriously. So check this out, and I'm over time, so really quickly. So functional programming and object-oriented programming are not like epic rivals, as Hacker News would have you believe. They're actually kind of BFFs, best friends forever. If you think about iconic object-oriented programming languages, you might think about Smalltalk, a language created by Alan Kay. And in Alan Kay's conception of object-oriented programming, the idea of objects is that they are message receivers. So they take in messages, which messages consist of like a method name and some arguments you want to pass to the method. And then the object gives some kind of response, which is up to the object. So if that's like the Alan Kay idea of object-oriented programming. In Lambda functions, functions are just things that receive an input and return an output. So that's not really that different, because both of these are basically representing things in terms of their behavior. Hopefully you can read that. So we're representing all data in terms of how it behaves, what it does with the inputs it's given. So actually what's pretty cool is that if you look at that language Smalltalk, if you look at how Booleans are defined in Smalltalk, they are things that take a first thing, an if true thing, and a second thing, an if false thing, and pick one of them. True picks the first one, and false picks the second one. Does that sound familiar? That's exactly how they look in the Lambda calculus. Now, we didn't do it with the fancy Lambda syntax, but this is the same thing as what we had before. Just replace x with if, or x with then, and y with else, and you get the same definitions that we just had. So this actually means that we can even create functional objects from the Lambda calculus. So I think that is pretty rad. Now, I'm super out of time, so this was just a preview, a little taster of the Lambda calculus. Go check it out on your own. I think the only way to wrap your head around this is to play around with it. The code from this talk and more examples is up on my GitHub gist. You can find the link in my Twitter. I just tweeted it out. And there's a bunch of other things here that you might want to read through about functional programming, about that weird object-oriented function thing that I just mentioned. So check out the references. So okay, that's it for me. Mulțumesc. Thank you so much. And I want to thank the organizers for having me back. Thank you.